not going to keep 90 degrees. It'll just go because it's pinned. Like the approximate shape. Like 90 here will not be. It'll just be like and then it'll just these guys will stop there because it's a pin.
So for they're different. We're going to talk about 3 applications for the virtual work present. 2 applications, we still teach them, but you probably will never use them again when you start working. But 1 application is used all the time, even though that you don't know that you're using it. The 3rd application is basically the obtaining approximate solutions, which is basically the finite element analysis method. The other 2 applications that you're studying in your courses are first solving for reactions in statically determinate beams, and the second application, which you probably study in other courses, is finding displacements at specified points for linear elastic small deformation beams. So both those applications are used. The virtual work method is used for those 2 applications. So for the first application, what we're saying is that this is true for every U star, for every Y star. This is true for every Y star. I'm going to choose Y star such that the second derivative of Y star with respect to x1 is equal to 0. Now, if I choose Y star such that the second derivative of Y star with respect to x1 is 0, I get rid of the first term. I'm only left with the external virtual work supplied by the reactions, or by the forces on the boundary. And we can do this to find the reactions. But since Y star can only have 3 components, actually, what am I saying? Okay, well, let's see how we can use this to find the reactions. We already know, given a force here P, and for this particular beam applied at a distance A, I know that the reaction here is equal to PA over L. The reaction here is equal to PB over L. And the reaction here is 0. Just by the sum of moments. Sum of moments equals 0, sum of forces equals 0, you get those reactions. Now I'm going to find those reactions using a different method, by simply applying a virtual displacement that has 3 components. The first component is a horizontal displacement of x1 star, and the second is a y star, a vertical displacement. This vertical displacement is equal to y1 star at the first point plus x1. This is x1 sine theta. Because theta star is constant and y, you're going to get to the second derivative of y star is 0. d2y star by dx1 squared is equal to 0. Which allows me to say the integral of qy1, qy star and all. So the only thing that I have is p, the external virtual work, is equal to negative p y2 star. Negative because p is downwards, y2 star is upwards. The reaction 1 multiplied by y1 star. The reaction 2 multiplied by y3 star minus the reaction R3 multiplied by x1 star. And I'm saying that this is equal to 0. So negative p y2 star. Now y2 star is equal to y1 star plus x1 is equal to a sine theta star plus r1 multiplied by y1 star plus r2 multiplied by y3 star. Y3 star is equal to y1 star plus L sine theta star minus r3 x1 star. Again, this is equal to 0. I'm going to group the terms according to the multipliers. Because I assume 3 displacements, I get the following 3 terms. And what we're saying is that this is true for every y star, for every x1 star, for every theta star. This is true for every starred component. What does this tell me? It tells me if I assume theta is such that sine theta is 0 and x1 0, I get the first equation. If I assume this is 0 and x1 0, I get the second equation. If I assume this is 0 and this is 0, I get the third equation. So, because we're saying that this is true for every one of these, you get R1 plus R2 minus P equals 0, which is sum of forces equals 0, basically the equation, and negative PA plus R2L equals 0, which is basically the sum of the moments around A or around point 1 equal to 0, and the third equation, R3, sum of forces in the horizontal direction equal to 0. So this is the first application of, and it only works for statically determinate structures. If you try it for statically indeterminate structures, you won't be able to find a solution because there's going to be more unknowns than equations. You have another example, you can look at the other example. Now another application that was very successful and was used and perhaps still used by people working in, like, professionals working in structures offices, but they've been working there for hundreds of years. The other application is to find displacements and specific points. Now, if you have a computer software, you just put your structure in the computer software, you use the stiffness method, and you find the displacement at every point. This method is used to find this displacement at only one point. You do a lot of calculations, and you end up getting a displacement at only one point. So how does this work? Well, if I have a statically determined structure, with loads, and a displacement field y, I'm actually going to call this y star. if I'm interested in the displacement at this point, I'm going to put here 1. And I'm going to apply, and I'm going to call this displacement field Y. Now the principle of virtual work states the following. From Y, if I put an extra Y star, then the internal virtual work is equal to the external virtual work. The nice thing about this Y star is that at the boundaries it's equal to 0, so there's no external virtual work on the boundary where there are reactions. And so I can simply say, applying the principle, EI d2y by dx1 squared multiplied by d2y star by dx1 squared integrated over dx1 from 0 to L will be equal to P, which is 1, multiplied by delta star, which is the displacement I'm looking for. This is delta star, which is basically the displacement at this point. Now, since this is a statically, these work for statically determined beams, that means bending moments are readily available, which means the term EI d2y by dx1 squared and the term EI d2y star by dx1 squared, these functions, I already have. Because I already have them, I can just input them here, and you get this equation that says m naught m1 over EI dx1 is equal to 1 multiplied by delta star. You know the bending moment, you know the bending moment, you know EI, you integrate the two bending moments, and you get delta star. And you probably are doing a lot of this in your you're doing a lot of this in your other courses, so I'm not going to go over it. I care more for finding approximate solution. The application, the virtual work method is used more for as an application for or as the basis for finite element analysis softwares. So as we, who's taking 665? So basically it's the same example that we started. So do you guys want me to go over it or no? So, no. Well, I'm not going to go over it all. I'm just going to quickly just go through it. Basically, to find an approximate solution to any problem, the only reason I'm not getting any response, so I'm assuming some people want to listen. So I'm just going to go over it. So, to find any approximate solution to any of these problems, you have to assume something. So we're going to use a cubic polynomial approximation and the virtual work method to find the displacement shape for the shown beam. Now to assume an approximate displacement, y is equal to a naught plus a1 x1 plus a2 x1 squared plus a3 x1 cubed. And I have four unknowns that I'd like to find. And I will use the virtual work principle to find those unknowns. First, I would like to satisfy the boundary conditions, which are the reaction at x1 equals 0, y is equal to 0, and at x1 equal L, y is equal to 0. So you end up with the equation that the approximate displacement that you're trying to find actually has a simpler form, which is a2 x1 minus L plus a3 x1 squared minus L squared. And so I have two unknowns. I would like to use the virtual work to solve for this problem. Now the virtual work principle states the following: the integral of ei d2y by dx1 squared multiplied by the second derivative of a new displacement called dy star dx called y star is equal to the external virtual work, which in this case is equal to r1 y1 star plus r2 y2 star minus p y3 star, where y3 star would be the displacement here, and everything is assumed positive, and an r3 multiplied by x1 star, for example, but this is 0 anyway. And so what should I assume? So I need to assume, now this is true for every y star. But I'm going to choose y star that does the following. Make sure that I get rid of those reactions. I don't want to see them in the equation, number one. And number two, has enough terms that I can solve for A2 and A3. So choose y star having the same form as y. Okay, y star is equal to A2 star and this ensures that y star 1 is equal to y star 2 is equal to 0. So I get rid of the reactions in that equation. So external virtual work will only be equal to negative p, the load, multiplied by y3 star, which is the y star when x is equal to L over 2. And when you substitute in equation, in virtual work equation, you end up with a term, a huge term, multiplied by A1 star, so A2 star, plus another term multiplied by A3 star, equal to 0. Equation 1, equation 2, find A2, A3. Because this is true for every A2 star. For every A3 star, I can choose anything for A2 star, anything for A3 star. Choose A3 star 1 and A2 star is 0. You get the second equation. Choose A3 star is 0, A2 star is 1. You get the first equation. You have two equations in the two unknowns that I'm looking for, and the two unknowns that I'm looking for are A1, A2, and A3. And as we talked about before, the principle of virtual work. Right. As we talked before, the nice thing about an approximate solution is even though the exact solution is a function that is not differentiable, the shear, which is the third derivative here, looks like this. The approximate solution will maybe look more something like that. So it doesn't really deal with this continent. And the more terms you use, the better an approximation you'll get. So a few notes about the principles of minimum potential energy. So everything we talked about was basically the virtual work applied for beams and applied for continuums. In the very first beginning of this lecture, we introduced the potential energy of a system, and we said that the equilibrium equation in a one-dimensional system is equivalent to minimizing something we call the potential energy of the system. But we just did it for one-dimensional objects, for systems with 1 degree of freedom. And we're going to talk about the same thing for systems with infinite degrees of freedom, which are basically the continuum. So, as we talked about at the beginning, there are 3 different types of equilibrium. We have stable, neutral, and unstable equilibrium. A stable equilibrium is the equilibrium in which the potential energy is minimum. When you perturb this cylinder, inside that big cylinder, when you perturb its equilibrium position, if you move it to the left or the right, it's just going to roll back to its equilibrium position because it has the minimum potential energy. If you perturb the cylinder horizontally, it's not going to come back because this is a neutral, it's current. All these positions have the same potential energy. This kind of equilibrium, even though the vertical force from the weight has a reaction, and the sum of forces in the horizontal direction is 0, so there is an equilibrium here, yet it's unstable equilibrium. The reason why it's an unstable because this equilibrium, compared to all the possible equilibrium positions, has basically a maximum potential energy rather than minimum. Because it has a maximum potential energy, the moment you perturb it, it has a potential to move to another state, and so this is an unstable equilibrium. Now, in cases like this, we are going, in cases when the equilibrium is stable, I'm interested in approximate solutions to the equilibrium equations using the fact that the energy is minimum at this position. So, I'm just going to quickly remind you what we did when we had a 1 degree of freedom system. When we had a 1 degree of freedom system, we said we have an equilibrium equation. And we had something called the potential energy of the system. Function of x. And what we found is that the partial potential energy of the system with respect to this x, which was the extension, ended up being equal to 0, and ended up actually being equal to the equilibrium equation. And we found that the second derivative with respect to x squared is greater than 0, that's why it's minimum. Now, the same will apply for a continuum. We're going to introduce something called the potential energy of system. And this was, we did it for 1D. Now here we're going to do it again for infinite dimensions. The potential energy of system, function of a displacement u. The partial potential energy with respect to this u will actually be equal to the virtual principle, which happens to be equal to 0 at equilibrium, and we just said that the virtual work is equivalent to equilibrium equations. And then the second derivative of potential energy with respect to y squared will be greater than 0, which means the potential energy is minimum at equilibrium. So how are we going to do this? I'm going to introduce a potential energy of the system as the integral of the internal energy in the continuum which is equivalent to the energy inside the string minus the work done by the external forces. What are the external forces? I have rho v and I have Tn. Now, I'm going to say, take the first variation of the partial potential energy. Now, depending on what the internal energy is function of, if you're using W, it's function of lambda 1, lambda 2, lambda 3. If you're using the linear elastic, it's function of the strains. So it really depends on what the internal energy, what the variables of the internal energy are. But let's just assume that it's function of the strains, epsilon ij, multiplied by partial epsilon ij. Or during equilibrium, or at equilibrium, we know that any perturbation from the equilibrium, the external virtual work, is equal to the internal virtual work. The stress, sigma ij, multiplied by any epsilon star ij integrated over the volume, is equal to the external virtual work, which is equal to rho v star, plus the integral of Tn dot u star dv. And so because this is true, at equilibrium, at the equilibrium stresses, at the equilibrium, the stresses that are in equilibrium with these external forces, and we know that the stresses are derived from partial u by partial epsilon ij. So you end up with the fact that the potential energy at equilibrium, so at equilibrium, first variation of the potential energy is 0. Therefore, potential energy is minimum, maximum, or neutral at equilibrium. And to know whether it's minimum, maximum, or neutral, you take the second variation. And in fact, because the external forces are not assumed, so this will be 0. Because external forces are assumed to be constant, i.e. not function of position. And so it really depends if it's stable or not. It will really depend on this. It has to be greater than 0. And for this to be greater than 0, basically we talked about this before. That's the stiffness of the material. The stiffness of the material has to be positive definite. If the stiffness of the material is positive definite, then the material is stable. So this has to be positive definite. For the material to be stable. So, just a note about the difference between linear elastic materials and elastic materials with large deformation. For the potential energy functions for linear elastic materials, everything that we, when we derived these principles, let's look at the small deformations. Let's just look at the principal work. We used the small axis, which is the variables in the current configuration, to define epsilon star. Now, because in small deformations, epsilon star small deformations, epsilon ij is equal to half partial ui by partial capital xj plus partial uj by partial capital xi So under small deformations, this works. But under small deformations, so I can use the small strain matrix to use it for the potential energy. Watch. So I can make my potential energy as equal to function of epsilon ij minus the work done. And usually we use linear elastic materials. Minus the work. Linear elastic materials constitutive function. Minus the work done by external forces. this string, the principle of minimum potential energy works to find solutions, but these solutions are not, I cannot use it to find solutions to buckling problems. So I cannot use this principle of minimum potential energy to find the buckling of a bar, for example. Because the constitutive law, the constitutive law is function of the small strains, and the small strains, once an object starts rotating, will punish this object by saying you actually require a lot of energy to rotate. And because we're saying that the object will require a lot of energy to rotate, I'm actually increasing the energy. So usually buckling will be associated with higher potential energy, and that's why these systems with linear elastic materials with small deformations are not able to predict buckling. For large deformation materials, the function here is function of lambda 1, lambda 2, and lambda 3, minus the work done. These are functions for lambda 1, these are functions of lambda 1, lambda 2, and lambda 3, and so they do not punish a material when it starts rotating. When the materials, these are the functions that we talked about, functions of the Mooney-Rivden material model, for example, or any function of lambda 1, lambda 2, lambda 3, they do not punish the material if it starts rotating. If an object starts rotating, it does not require additional energy. The energy is only function of the stretches of the material. Because the energy is only function of the stretches of the material, I can model buckling, or I can model anything that has large deformations and has any type of large rotations. And so we're now going to use the principle of minimum potential energy to solve, to find approximate solutions. And so I'm just going to go through this really quickly, perhaps just show you two examples that we already did in 665. I'm going to write the potential energy of the system, minimize the potential energy of the system to try and find the approximate solution. So we're going to do this for two types of beams. The first one is a beam under axial load, and another beam under lateral load. Now the Galerkin and the other approximate methods, this is not covered in 665. But it's covered in 665. I mean, you know all these things. But I'm not going to ask you about it in exams. Alright, so how can we use the principle of minimum potential energy to find approximate solutions? So, for this problem, we need to find the horizontal displacement of the body, of this bar, and assuming polynomials, assuming horizontal displacement function as a polynomial of degrees 0, 1, 2, and 3. Now for degree 0, if we assume that u is equal to v naught, unacceptable, as we talked about that before, because the boundary conditions cannot be satisfied. except by the trivial solution. And if I say U is equal to A naught plus A1 x1, and satisfy boundary conditions, therefore A naught is equal to 0. So the displacement is equal to A1 x1. Write the potential energy of the system. The potential energy of the system is equal to the potential energy of the bar, sigma on 1, epsilon 1 over 2 integrated over the volume, minus the work done by the external forces. The only external force I have is P. So multiplied by displacement at x1 equal to L. So the potential energy of the system is equal to, so epsilon 1 is equal to A1, sigma 1 is equal to P epsilon 1, which is equal to E A1. So this is equal to E A1 squared. dV is equal to the area of the bar multiplied by that end. So this is the potential energy of the system. At equilibrium, the potential energy of the system is 0. Is minimum. The only variable is A1. Therefore, let's just do the integration. This is E A1 squared AL minus B A1L. And so this will be equal to 2 E A1 AL minus BL equals 0. And so A1 will be equal to P over 2EA. And so U, the solution, the approximate solution, therefore, approximate solution U is equal to P divided by 2EA x1. And repeat for other terms. Repeat for other approximations. So we've already done this many times at the beginning of 665, so just do it again here for 664. And the difference is, you should now perhaps understand what we're doing a little bit more. Now for a simple beam, or for a beam under lateral loading, the only difference is the form of the potential energy that we're using. The potential energy of the system for this beam is equal to the integral of EI minus the work done by the external forces. So the only difference is the form by the external forces. The only difference is this potential energy of the system. Its function of, this is basically equal to m over 2 multiplied by the first derivative, or the second derivative of y. and the moment is, which is basically, it comes from the stress multiplied by the strain, sigma on 1 multiplied by epsilon on 1 integrated over the beam. So this becomes EI over 2, the second derivative of y with respect to x1 squared, all squared. So again, minimize the potential energy and find whatever approximate solution you want. You assume something for y, minimize the potential energy of the system to find this one. So now you're required to solve the last 2 questions in the previous assignment and 1 question for this approximate solution. It's basically 2 beams under one under axial load and one under lateral load, and hopefully you still remember what you did in the first assignment for 665. All right, so this is it for this part of the course. Starting next week, we're going to talk about plasticity, and I'm going to have a handout that I'm going to post on eClass. I would recommend that you download it before and maybe try reading it before we actually start in the next lecture. I will post it probably during the long weekend, so by Monday it's going to be there, not before. Any questions? Okay.